Life sciences is an enormous field of study that examines every living thing on Earth. So from bacteria to begonias or to beluga whales, life sciences aim to learn everything about life on this planet. There are obvious practical reasons that the life sciences are valuable. The study of life sciences lends to important insights into disease processes and allows the development of novel therapeutics and innovative medical devices, thereby directly improving human health. Life sciences study the biology of how these organisms live, which is why you may hear, the group of specialities, this group of specialities referred to as biology. Welcome, everybody. I'm Pratima Penumarthy, founder and director of Aryamath Academy. Our academy, in collaboration with Shravio, we proudly present STEM Talks. In this talk show, we will introduce you to fascinating people who very passionately inhabit scientific and technical frontiers of our society. It's with tremendous pleasure that I welcome you all to our 7th episode of Aryamath Academy's STEM Talks. Today's STEM Talk is with Dr. Max Narovlyansky. He completed PhD in biochemistry from Harvard University in the year 2011, and he's the founder of Flowcell. He has created a marketplace for precision medicine tools and services. His company focuses on micro-physiological systems, single-cell platforms, and bioinformatics solutions. A little more about Dr. Max. There's a lot about him, but I just want to share a few of things about him. Is that he has synergy of skills for design, manufacture, and using of medical devices. He has specialized knowledge in point-of-care devices using microfluidics with variety of detection methods. He is into the development of cost-effective processes and root cause. I don't know the exact name for that investigation, which Dr. Max can tell us eventually. He has done data analysis and interpretation, algorithm developments, and some process controls, most like Six Sigma. He has experience with regulatory environment and clinical study administration. Apart from that, he's also having amazing specialty in immunodiagnostics, microfluidics, biochemistry, data analysis, clinical testing, in vitro diagnostics, point-of-care diagnostics, oncology and drug development, and companion diagnostics and precision medicine. Thank you very much for having you've been having today. We are so glad to have you in our team today, Dr. Max.
Thank you so much for having me. It's a pleasure.
So Dr. Max, today our topic will be all about precision medicine. So this particular program will be excellent for all the undergrads, the upcoming graduates, also students who are high schoolers who are planning to get into their careers in life to get more information, more ideas about precision medicine. So to begin with, Dr. Max, what is the state of precision medicine today, and when can we provide the right drug for the patient?
Great question. Precision medicine has made significant advances, and we've heard a lot about the development and evolution of genomics. And indeed, in the field of research, it has revolutionized our understanding of oncology. For example, some of the techniques that you mentioned with single cell analysis, they intrinsically require miniaturization and microfluidics to get down to that single cell level. These tools have been in existence, but largely have been the purview of research, such as flow cytometry. So part of the effort is to move them into the clinic. Also, the microphysiological systems that you mentioned, they provide ability to model and understand disease conditions. So that is the next step of precision medicine, moving from genomics to model systems that encompass biology with fuller complexity. And just to touch upon a topic for the future, that's, I think, intrinsically something that can be called biocomputation, because the integrity of the disease condition, especially if you consider neurodegenerative diseases, They require oftentimes biology that includes nerve and muscle cells, and also systems to evaluate their ability to communicate. So that's beyond genomics, right? So this is where the field is going, but it has been a big challenge because a lot of advances have focused on drug development. And microfluidics has been the Cinderella at the ball, but it is in fact the princess.
Oh, I see. So, yeah, Dr. Max, what are the current limitations for when you talk about precision medicine?
As I was just saying, the Cinderella needs to be empowered. These common tools have been slow in coming, and it requires technical, overcoming technical challenges as well as regulatory and economic challenges. The reason we've made a marketplace, as you've pointed out, is that to a significant extent, the technical challenges have been overcome. Not entirely, but we have capabilities for research, as I was saying about flow cytometry, that have not been applied clinically. And this is especially the case for these more advanced models of disease that use tissue. Again, microphysiological systems implies the capability to replicate with fidelity the disease state. That has been severely lacking. We've been living for several decades in a two-dimensional world. So that's rather limiting when you work with a flat human on plastic, essentially.
Oh, and then what do you think is the difference between this companion and complementary diagnostics?
These are closely related and may sound identical, but in fact, the FDA has issued guidance in 2016 and 2019 talking about this differentiation. So they haven't provided the full guidance that we want, as I was alluding, in terms of regulatory approval and reimbursement, but they have provided some information, including terminology. So companion diagnostic is a bioassay that measures some relevant biological entity that tracks with progression of disease or predicts when a treatment will work. And in fact, it's specifically tied to the drug. And just thinking about the integrity of the process, pharmaceutical companies are the ones paying for the research and clinical trials, which are extremely expensive. So they drive the process, and the diagnostic is wedded. It's a companion to the drug. So if you really think about it, it's a drug in search of the right patient, which is different from a patient in search of the right drug. And that's what complementary diagnostic means. A lot of drugs out there, in fact, the majority, do not have biomarkers. But just to give a sense of where the field is going, now there is encouraging guidance from FDA to implement biomarkers from the early stages of drug development, not just to use them to rescue a failing drug by finding the proper target population. So over a third of new oncology programs now have a companion diagnostic program built into the beginning. But still, that's going forward. Where we are now is only a fraction of drugs out there have these companion biomarkers. What about others? And also, if want to flip it to the perspective of the patient, when you are rejected by the biomarker for the drug, what then? So complementary diagnostics addresses this problem by especially the use of tissue. Which can predict drug response directly. So genomics informs the likely treatments with other, disease factors, and then out of those possible lines of therapy, instead of rolling the dice, we can directly predict drug response by testing tissue with different treatments. So that allows us to put the patient in the center and to ask which of the likely drugs will work, and also let us score them. How well do they work? And that's extremely powerful and broader than complementary diagnostics, than companion diagnostics at this time.
Okay, yeah. So then what is the actual tension between the personalized and precision medicine?
It's a very good follow-up question related to the previous one that you just asked about the flavors of diagnostics. Precision medicine generally means um, uh, um, what I was describing as the companion diagnostic.
Yeah.
What is currently available? Personalized medicine is focusing on the needs of the patient. So it may require going, in a certain sense, a little bit outside of the box um, um, and asking what are the patient's options. Technologies exist. There are, for our marketplace, we provide third-party services to try to address these needs, to take cancers of specific types that have been worked on by these innovators and to provide the prediction of response. So the tension comes from the deep involvement of economics in this challenge. It's not just healthcare and technology. Somebody has to pay. And the transition from research to clinic is a very important one. So the tension is that precision medicine that exists now works for large organizations like pharmaceutical companies. Once a drug is approved and is administered, it will be reimbursed. There is no grading curve. If it doesn't work for the patient, the first line therapy for cancer, second line therapy fail. Maybe it's with biomarkers, maybe it's without, there is total reimbursement. The tension is that it doesn't work for the patient. Unfortunately, we know cases where this experience weakens the patient. And instead of finding the right therapy, which may be third or fourth line, or maybe no line at all, but it exists and can be found. The patient obviously is not at the center yet. And also in the very large scale, I would argue that clearly for the government, it's not efficacious to have insurance reimbursement of all of these treatments that don't look deeply into what's likely to work. We should emphasize that more rather than giving people $200,000 treatments that fail.
Very true. So another thing which is always, we have this question in mind. So what are the outcomes in outcome-based medicine, right? And what is that? And what does it mean for the patient population?
Personalized medicine is something that should usher in the age of outcomes-based medicine. That is something that is coming for financial reasons as well. As a country, United States spends almost 20% of its GDP on healthcare, which is about double what Europe spends. And the outcomes are not that much better. So the question then becomes, where is the 10% of GDP going that we're not getting the benefits of? And a lot of it is going into the development of new therapeutics. We are the world leader. Up till recently, we were responsible for about 50% of innovation in this field. I haven't looked at it in the last year. Hopefully, we're still up there, but we pay for it as well. We have the highest out-of-pocket reimbursement, in the world, about $6,000 per every man, woman, and child. So the outcomes are not commensurate with the input, and that's a misallocation of resources. Rather than reimbursing drugs only all the time, we should incentivize them with a grading curve. And that will also mean better outcomes for patients, because the drug developers and even hospitals providing this care, their interests will be aligned by saying, in this type of cancer, this is the expected performance. If you can save this person or do better, you will get an A+. And that's in terms of money, because that's what will ultimately, again, provide that alignment and also help to pull a lot of advanced clinical tools into research. There isn't yet, again, this alignment for personalized medicine, right, and outcomes-based medicine, and that's I think this complexity that is so fascinating and yet so challenging in this field. There is microfluidics, there are advances in biology, but there is also a very important connection with a regulatory and reimbursement angle. And this alignment that I speak of, it's a very major kind of view. I know that large organizations that provide consultancy in this field also see this outcomes-based medicine coming, not from the technical side, as I largely see, but just the economics are such that we cannot sustain it. And in fact, I'll give an example. There's an organization, a non-government organization in Massachusetts, that was advising about some drugs, and they took 5 drugs from this particular disease and made recommendations for price adjustments. And I did the calculations. They were recommending a decrease of pricing of about 70 to 80% on average. So that's where they feel the pricing belongs. And in order to make that business model work, we need better technology, but also this better alignment. Insurance is coming around, but I think we need regulation, awareness of the public, and maybe politicians need to get involved to really help with this alignment of this new paradigm. Let us be graded on a curve.
Absolutely. A very nice answer, Dr. Max. And what do you think is the role? Because now we talk about so much with artificial intelligence. So what is the role of AI in drug development?
Drug development is a very challenging business. Also, it's been quite inefficacious for several reasons. One of which is the lack of these microphysiological systems. Imagine a flat human, right? And then doing drug development on that model is very limiting, to say the least. So we need to advance the pre-analytics in order to really provide the representative data to AI in quality of, again, physiological fidelity and in quantity. But about the quantity also, just to maybe give us a couple of numbers. A single, well, we have obviously 3 billion base pairs in the genome, which constitutes about 20,000 genes. People were actually surprised that the number was not higher. And they encode about 100,000 proteins. And then, of course, there are metabolites. There's also mitochondrial DNA, which is quite separate. And then there is systems complexity as it builds up. So the reason I give you these numbers is that these are all entities in the analog computer that are interlinked. It cannot be decoupled. Imagine trying to solve a system of differential equations with 200,000 entities. You know, it's completely beyond our ken and mathematical capability. Quantum computing may start to get there, but it's vast. So we're nowhere near being able to predict it. What we need to do is to measure it. This concept of biocomputation is kind of key to that. And it's the prerequisite and prequel to AI. We don't just want to measure, you know, these intricate biological markers and information. We still want to understand and provide a much simpler, they call it a digital twin essentially. But mathematically speaking, it's a response surface. So from you know, 100,000 or 200,000 variables, it can be reduced to a few, maybe 3. Where we can predict, given some key inputs and some treatments, what the likely output will be without having to go to the biology. And this is where virtual screening for drugs comes in. So AI has a huge role to play in this field, and there have been huge investments. In fact, the largest area of investment of AI in AI last year was in total 13.8 billion was invested in startups. And it went this is specific to biology, which is the largest investment in any area of AI. So there's clearly recognition that drug development is inefficient and needs improvement, and belief, which is true to an extent, that better analytics is the answer. But the reason that the pace of development has been what it has been for the last 40 years is not just lack of machine learning, it's the lack of proper data. There are extremely bright scientists that have been working on, for example, neurodegenerative models. And when you look at the track record, and I was even speaking to some neurologists who do financing for large pharma, and they let slip that it pretty much never works. The challenge is so complex. There was a year I was looking at with the largest clinical trial failures, and out of the unlucky 13 at the top, biggest losers, there were 4 Alzheimer's drugs from large companies like Merck, AstraZeneca. These are not lacking in talented individuals with some ability to model and think through. So the AI is a little early, and to be candid, our marketplace also is struggling with this phenomenon that the recognition for microphysiological systems is early, but that is the prequel. Very important follow-on, but there needs to be more emphasis on data generation with pre-analytics.
True. So Dr. Max, coming to looking, just talking about some drug development models, what kind of advanced drug model or drug development models, that currently exist now?
There are some very sophisticated models. As I was describing, there are a few elements that come together. One is microfluidics, which is just miniaturized fluidics, representing the equivalent of vasculature. That is a key requirement for three-dimensional biology, which is where the field is moving now, not just in research, but clinically. They're trying to move there, or I should say in the preclinical development. The limitation that the field is experiencing is that without the equivalent of vascularization, the tissue cannot live. We live in an oxygen-rich atmosphere, and the main requirement for biology is actually oxygen. Before nutrients and other elements come in, that is the key limitation. And this can be traced throughout history. For example, during Carboniferous, with more oxygen, there were bigger insects because of the limitations of vascularization and delivery of blood. So the concentration of oxygen affects the physics of biology through the ability to deliver oxygen. So these systems are very important, especially, as you were saying, in complex models. For example, the brain, the most oxygen-hungry organ. When we run, the reason the heart starts pacing is that the brain needs to keep up the oxygen level. It perishes within a minute, right after oxygen supply is cut off. So that's extreme sensitivity. Also, it's a three-dimensional structure with many different cell types. For example, neural cultures require supporting cells, so that's quite complex. And finally, there's a lot of wetware. There is the matrix in which cells live, which is very impactful. It informs their behavior. Also, it's of great significance in cancer metastasis because it has a retaining effect. So these elements need to come together for advanced models. But let me give you one very specific example of how these come together. This is from a model that has been developed by James Hickman, who is the CSO of Hesperus. He actually is kind of I'll set aside stories about Dr. Hickman. He's a very accomplished man, but the systems that they built is perhaps little bit too sophisticated for biologists to use. That's why they provide it as a service in the contract research organization business model. Their focus is neurodegenerative diseases such as Parkinson's, ALS. In ALS specifically, this is something I worked on as a postdoc. There is a lot of pathological processes that are known to occur in the neurons. There are also some in the muscle, but it's actually the communication between them through the neuromuscular junction. So that two-cell complexity needs to be replicated on this microphysiological system in the chip. The nerve is stimulated, and they observe the response in the muscle. And they do it in a way that uses essentially nanotechnology. There is a laser beam which is reflected by a cantilever, a nano cantilever that's pulled by the muscle cell. So there is miniature lasers, there is this, tiny little deflector, and it's basically cell-sized, right? So that the cell can really, give a good range of response. So as you can see from this, it's got biological complexity, it's got technological complexity. So that's the modern age. As you can see, there is a place for engineers to help biologists.
Dr. Max, because just now you mentioned about this microphysiological system. So there are different type of technical expertise must be required for it, right, to develop it?
Yes. That's the fun part in the sense about the field. It's extremely multifaceted. It's an opportunity to collaborate across the fields or to embrace a few fields, which is something I've tried to do to kind of span several of these disciplines in order to be able to address this challenge. One needs to understand the requirements of biological assays, the biomarkers and the endpoints, to use the jargon of biologists, as a developer of these engineering systems. That has not always been the case. Also, the requirements of industry need to be considered. For example, in graduate school and elsewhere, there is a lot of usage and reference to microfluidic chips. That's wonderful, but very often it literally is some kind of a flow chip, a microfluidic device, which provides a single data point. That's fine for research, for a graduate student working on it, but not appropriate for high throughput analysis with robotics. So this has been a limitation, not to cast any shade, but certain companies have made decisions that may affect this acceptability, I guess I could say, by industry, the ability to utilize this. So, for example, a local company, Emulate, spun out of Wyss Institute. They've gone with microfluidic chips using PDMS technology, which is very challenging to make. It's a rather manual process, and also very challenging for handling with robotics. So it requires a lot of hands-on by the user. Time-consuming and also pricey. Other companies that we work with, like Tissues from Germany, they've also developed the chips with a particular station to thermostabilize them with integrated valves in the chips. But one of the interesting things that they've built is an entire lab product line which automates the handling of these devices. So they provide entry point devices which are smaller, less expensive, and the user can do some more manual work. But there are larger platforms that envision a whole pipeline, and they have robotics to move these chips around, but the chips have a different form factor from traditional multi-well plates. So that's a challenge to adoption by the industry. Although, so there's robotics, they can buy into that, but it's a different platform. To give the final company from Europe, company Mimitas, from mimicking a biology, they have made a very good technical decision for business reasons to adopt a format that looks like a 96 well plate. So it's possible for multi-pipetter robots to manipulate fluids in them, which is very important, especially for some biology that uses stem cells. They're very hungry and very needy, and need a lot of information that can change in order to differentiate into the proper adult cell type.
Thank you.
So to recap, I guess what I'm saying is it's really this integrity of knowing the reagents, the biology, as requirements to fulfill that technically. And even that's not enough because of what I was describing earlier, with a strong impact of regulatory and economic aspects.
And Dr. Max, because I know we were talking all about the precision medicine, but when we come to the personalized medicine, there must be definitely, more economic barriers too. So could you just elaborate more on that? I'm not sure what are the regulatory or economic barriers for that.
Yes, so there is an interesting barrier there. This is something I've been breaching as a topic with oncologists, some locally, about introducing these tools into the clinic. The challenge with reimbursement is we can predict a drug to save grandma from cancer, but sometimes the family needs to reimburse, right? But that's actually not good enough, as it turns out, because the current system is more facile with reimbursement by insurance. So rather than going for this personalized medicine with even self-powered reimbursement. And I know folks I've asked, those who've lost loved ones, would you, pay $10,000 to, be able to get this information, to test the drugs outside of the body in conditions that replicate the disease? The answer is invariably yes, as you can imagine, but it's an inconvenience to hospitals. So there is that tension, as we were saying before. Interestingly enough, I was speaking with a prospective customer from India. Because of different insurance structure there, there is a lot more embracement of reimbursement rather than reliance on insurance, especially for the more expensive procedures. That this may be more acceptable because there is this barrier that's artificial. People want this information that's life-saving, and the system tells them that you're inconveniencing us. So that's something that we need to overcome as a barrier here, but it may actually start to catch on faster elsewhere. There is more advanced acceptance in regulatory sense in Europe, and other countries may leapfrog us in certain sense.
And also, Dr. Max, because most of our viewers are all high schoolers now, we have undergrads who are also listening and grads. What would you recommend to all the students considering entering the precision medicine field?
It's a rich field. It's one that's necessary and will be with us for a long time. As long as there are humans, there will be need for precision and personalized medicine. So it's a great career choice. I would merely say that it's multifaceted. So there are many different ways to contribute. Right now, we're in relatively early stages, so there is more need for jack of all trade kind of understanding, which is what I've accumulated. But in time, there will be more specialization. So if you are in high school now, you may want to consider a more specialized element, although, as I was saying, there's this exciting interlinking of various fields, not just technical, but economic, regulatory, social. So There is a need for policy advisory. There's engineering. There is biology, biological innovation, working with stem cells to advance the field in the aspect of three-dimensional biology that really enables us to have realistic artificial models of disease. And this is very impactful, for example, for COVID vaccine development in respect to various mutant strains that have been occurring now. One of the articles I was reading, in the very abstract, they observed that this proliferation of mutants, which we kind of certainly anticipated, calls for more advanced animal models. And I think that's missing the point. This is a highly immune specific disease. It's highly personalized how people respond. Is it a light cold, or is it a severe case requiring hospitalization? So I think there's a great need in biological understanding. So this will perhaps be the really big problem. Right now, there is certain technical bottleneck as well as regulatory and economic, but I think longer term, biology is the ends. So
Right.
it is the, yes.
I
Technology, I would
actually,
say, is the means, biology is the ends. Although
that
it's also the means, that's where biocomputation comes in. It's not just a passive entity, it really needs to recapitulate the complexity in order to give us highly faithful physiological data to provide to AI. And then we can really understand the vagaries of disease with some single cell analysis to ensure that we treat it fully. It's like cancer with elimination of minimum residual disease. So lots of exciting jargon. Really just signifies the little bit of complexity in the depth. It's a very exciting field.
true. I also had some students who asked me, like, why should one consider a career in life sciences? The only thing I could say was, like, studying life sciences will provide you with the foundation of scientific knowledge, and you'll know the ways of exploring the world. The life sciences, they pervade in so many aspects of our lives, right from healthcare to environment, debates about stem cells research and all this genetic testing. Is there anything else you want to add, Dr. Max? I mean, that's what I would always say if someone says, why should I consider a career in life sciences?
I agree with you, but I would strengthen the argument. One can learn scientific approach with areas like physics, for example. It's very cerebral, but this is the century of biology. I believe that, and this is not just my saying. It stands on the shoulders of the predecessors, the developments in material science and computation. So they enable through, again, microfluidics, through ability to sequence genomics and really analyze massive amounts of data, to even begin to address the complexity of this analog computer. But besides finance or other areas, it's almost a question of where else are you going to go. There is, of course, technology, but I think biology will be prevalent, and one doesn't have to go very far to see the evidence. As a way of advertising our technology, in January of 2019, I came up with a game called Pandemic to kind of make the acute case for the need for these microphysiological systems, whereas cancer is more of a chronic condition. So I think the experience that we've all had with impact on every aspect of our lives from Corona shows just how central it is. And we are advancing in this field. So it's going to, biocomputation, in a word, is going to be a bigger and bigger part of lives. It's a combination, again, of a kind of analytics and biology.
Agree. Thank you, Dr. Max. Thank you so much, Dr. Max, for taking time for sharing about microfluidics, your different solutions for which is biologists, and your extreme passion for contributing to science and developing new theories. Any final advice that you would love to give to our, the viewers who are mostly students?
Yes, be fearless. It's not an easy field, and certainly there's a lot of need for maybe simpler in some way pursuits that are still very impactful, but it's one very noble, and I think there's a great future for careers there. So I would encourage you to consider.
True. I would say here to all the students that ask yourself, what's your passion? If you dream of making a difference in the world by developing a life-saving vaccine or medications like Dr. Max is doing, or pushing society into future with, breakthroughs in technology, career in life sciences that, would afford you all these opportunities. And honestly, with so many possibilities, across the dozens of fields, there is something for everyone. A couple of most common careers, which Dr. Max, you can agree with me, that include, you can correct me, Dr. Max, if I forget something, like biochemists, clinical research associates, research assistants, microbiologists. Then there are other lesser known yet very important career solutions too, that include biomedical scientists, biotechnologists, industrial pharmacists, and even computational biologists. So most of life science careers, predominantly they reside in the medical field. However, jobs like, there are jobs like even computational biologists that can span across many other fields, which is including computer science and ecology. So I would like to end this talk today by saying that all our episodes, they've mainly focus on various STEM-related subjects, as well as different career motivations, educations, and passions. So I would say all the viewers to please think of us as, again, outlines in science. So tune into our show, and if you would like, please write a review of the STEM talk on our YouTube channel, Aryamath Academy Online, and don't forget to subscribe and spread the word. Thank you very much. Have a nice day. Bye.